Hello, I am N.Kripa, Assistant Professor, Department of Biomedical Engineering from Bharat Institute of Higher Education and Research, Chennai 73. We are going to see about the course Biosensors and Measurements, and the topic we are going to cover is photoelectric sensors. So, as the name implies, all these sensors and instruments which we are going to see uses light. And we are going to see some of the examples of the photoelectric sensors which are being used in biomedical field. So the first example we are going to see is the photo tube. Please refer to the diagram which is on your left hand side. So that is a photo tube. A photo tube or a photoelectric cell is a type of gas filled or vacuum tube that is sensitive to light. Such a tube is more correctly called a photoemissive cell to distinguish it from a photovoltaic or photoconductive cell. So there are three categories of phototubes: gas, vacuum, and electron multipliers. The basic phototube is made up of gas-filled or vacuum electron tube in which two electrodes, that is the cathode and an anode, are mounted. A gas phototube utilizes argon or some other type of inert gas at a very low pressure. The electron multiplier is a modification on the basic gas and vacuum phototube. In addition to the two electrodes, this type of phototube is also equipped with a series of metal discs called diodes. The diodes are arranged inside the electron tube to amplify the emission of electric current. Now coming to the construction, the surface of the cathode is a phototube is typically coated in a cesium or some other type of photoemissive material. The coating is extremely sensitive to light in ultraviolet, near infrared, and visible ranges of electromagnetic spectrum. The phototube works by means of a process called the photoelectric effect. Through this process, when the surface of the phototube's cathode is exposed to light, it emits electrons, and these electrons are attracted to the positively charged anode, creating an electric current. The light wavelength range over which the device is sensitive depends upon the material used for the photoemissive cathode. A cesium antimony cathode gives a device that is very sensitive in the violet to ultraviolet region, with sensitivity falling off to blindness to red light. The cesium on the oxidized silver gives the cathode that is most sensitive to infrared to red light, falling off towards blue, where the sensitivity is low but not zero. Vacuum devices have a near constant anode current for a given level of illumination relative to anode voltage. The gas-filled devices are more sensitive, but the frequency response to modulated illumination falls off at lower frequencies this compared to vacuum devices. The frequency response of vacuum devices is generally limited to the transit time of the electron from cathode to anode. Now coming to the applications and advantages and disadvantages of phototubes. The phototube can be divided into three general categories: control, measurement, and audiovisual reproduction. So under control, the light sensing application such as burglar alarm system, automatic door opener, the traffic light controls, measurement functions include these the use of color temperature pyrometers, while audio visual reproduction application include theater sound system and pinball games. In a burglar alarm system, for example, a phototube and a beam of light are used as a part of electric circuit. The beam of light is directed onto the phototube, which is installed some distance away. This may happen, for example, if a burglar jumps open the door, the broken circuit will in turn cause a relay to close, sounding the burglar alarm. Phototubes were previously more widely used but are now replaced by many applications by solid state photodetectors. The photomultiplier tube is one of the most sensitive light detectors and is still widely used in physics research. One major application of the phototube was the reading of optical soundtrack for photo projected films. Phototubes were in use in a variety of light-sensitive applications until they were suspended by photoresistors and photodiodes. And some of the advantages of phototubes are they are simple in construction and it is very cheaper. And some of the disadvantages of phototubes are they are very less accurate and the band pass is also more. Next, we can see about the next most important kind of instrument called scintillation counter. So this is the diagram of a scintillation counter. Please refer to the diagram. We have a light photon through which one by one a photon enters. It's called a entrance window. Next we have a photocathode. Then we have a photoelectron. Then we have diodes. Then we have a fully it's been covered by glass envelope. Inside the glass envelope it is a vacuum filled, so no gas is there. And then we have an anode at the other end, and it has all been connected to the out given as the output signal. So everything has been connected by high voltage power supply. So this is the basic construction of a scintillation counter. A scintillation counter is an instrument that is used for measuring ionizing radiation. It comprises of the scintillator that generates photons in response to incident radiation. A PMT tube is used to convert an electronic and electric signals to process the signal. A scintillation counter or scintillation detector is a radiation detector which uses the effect known as a scintillation. Scintillation is a flash of light produced in a transparent material by the passage of particle, an electron or alpha particle or ion or high energy photon. Scintillation occurs in scintillator, which is the key part of the scintillation detector. So in general, a scintillation detector consists of a scintillator which has generates photons in response to incident radiation. Then it has a photodetector where a sensitive photodetector, usually a photomultiplier tube, a charged coupled device, CCD, a camera, and a photodiode, which converts the light to an electrical signal and electronics to process the signal. So the basic principle of operation involves the radiation reaction with a scintillator, which produces a series of flashes of varying intensity. The intensity of the flashes is proportional to the energy of the radiation. The feature is very important, and these counters are suited to measure the energy of gamma radiation, gamma photoscopy, and therefore can be used to identify gamma emitting isotopes. Now, coming to the principle of operation and working, the operation of scintillation counter summarizes as follows. The scintillation counter, which is the principle of operation, and then the ionizing radiation enters the scintillator and interacts with the scintillator material. This can cause the electrons to be raised to an excited state. For charged particle, the track is the path of the particle itself. For gamma rays, like uncharged particles, their energy is converted to an energetic electron through either the photoelectric effect, Compton scattering, or pair protection. The excited atoms of the scintillated material de-excite and rapidly emit a photon in the visible or near visible range of light. The quantity is proportional to the energy deposited by the ionizing particle. The material is said to be fluorescence. Three classes of phosphorus are being used. One is inorganic crystal, second one is organic crystal, and third is plastic photophores. The light created in the scintillator strikes the photocathode of a photomultiplier tube, releasing the most photoelectron per photon. Using a voltage potential, the group of primary electrons is electrotically accelerated and focused so that they strike the first dynode with enough energy to release additional electrons. These secondary electrons are attracted to and strike a second dynode, releasing more electrons. This process occurs in the photomultiplier tube. Each subsequent dynode impact leakages further electrons, and so there is a current amplifying effect at each dynode stage. Each stage is at a high potential than the previous to provoke the accelerating field. Primary signal is multiplied, and this amplification continues through the 10 to 12 stages. At the final dynode, sufficient electrons are available to produce a pulse of sufficient magnitude of further amplification. This pulse carries the information about the energy of the original incident radiation. The number of such pulses per unit time also gives information about the intensity of radiation. Now, coming to the applications of the scintillation counter, scintillation counters are widely used in radioactive contaminations, radiation energy survey meters, radiometric assay, nuclear plant safety, and medical imaging that we are used to measure radiation. There are several counters of mounted on helicopters and some pickup tracks for rapid response in case of security situations due to radioactive waste or dirty bombs. The scintillation counters depends on weighbridge application, fight terminals, scrap metal yards, border security, contamination monitoring of nuclear waste and ports. So it is widely used in screening technologies, in vivo, ELSA, alternative technologies, cancer research, and cellular research. It is also used as applications in protein interaction and detectors, academic research, and pharmaceuticals. Liquid scintillation counter is a type of scintillation counter that is used for measuring the beta emission from the nucleus. Now, there are some of the pros and cons, that is advantages and disadvantages. Efficiency. The advantage of scintillation counter are its efficiency and the high precision and counting rates that are possible. The later attributes are composed of the extremely short duration of the light flashes from the about 10 to 9 organic scintillation to 10 to 6 inorganic scintillation seconds. Spectroscopy, the intensity of the flashes and the amplitude of the output voltage pulse or the energy, as well as the number of the exciting particles, that is like gamma photons. For gamma spectroscopy, the most common detector inside this is sodium iodide, NAI, scintillation counter, and high purity germanium detectors for accurate energy determination. On the other hand, if a perfect energy is being required, we have to use germanium based detector such as the HPG detector. Now, some of the disadvantages of the scintillation counters are hygroscopicity. A disadvantage of some inorganic crystals, example like NaI, there is hygroscopicity, that is a property which requires them to be housed in an airtight container to protect them from moisture. And next, NaITI has to be beta or alpha response and poor low energy gamma response. Next, the liquid scintillation are relatively cumbersome. So these are the advantages and disadvantages of the scintillation counter. Next, we can see about the photomultiplier tube. So this is the photomultiplier tube. You can please refer to the diagram. A photomultiplier tube useful for the light detection of very weak signal is a photoemissive device in which the absorption of a photon results in the emission of electron. These detectors work by amplifying the electron generated by the photocathode exposed to a photon flux. Now coming to the construction and working of a photomultiplier tube, photomultipliers are typically constructed with an evacuated gas housing using an extremely tight and durable glass to metal seal like other vacuum tubes containing a photocathode, several diodes and anodes. Incident photons strike the photocathode material, which is usually a thin vapor deposited con- conducting layer on the inside of the entry window of the device. Electrons are ejected from the surface as a consequence of the photoelectric effect. These electrons are directed by the focusing electrode towards the electron multiplier, where electrons are multiplied by the process of secondary emission. The electron multiplier consists of number of electrodes called diodes, and each diode is held at a more positive potential by approximately 100 voltages than the preceding one. A primary electron leaves the photocathode with the energy of the incoming photon of the 3 eV for blue photon minus the work function of the photocathode. A small group of primary electrons is created by the arrival of the group of initial photon. The primary electrons move towards the first diode because they are accelerated by the electric field. They each arrive with approximately 100 eV kinetic energy imparted by the potential difference. Upon the striking of the first diode, more low energy electrons are emitted, and the electrons are in turn accelerated towards the second diode. The geometry of the diode chain is such that our cascade occurs with an exponentially increasing number of electrons being produced at each stage. Now coming to the applications of this, photomultipliers are the first electric eye devices being used to measure interpretations in beams of light. Photomultipliers are used in conjunction with scintillation to detect ionic radiation by means of handheld and fixed radiation production instrument and particle radiation in physics experiments. Photomultipliers are used in research laboratories to measure the intensity of spectrum of light emitting materials such as compound uh, semiconductor and quantum dots. Photomultipliers are also used detectors in many spectrophotometers, and this allows an instrument design that escape the thermal noise limits sensitivity, on which therefore substantially increase the dynamic range of the interactment. Photomultipliers are used in numerous medical equipment designs, for example, in the blood analysis devices used for clinical medical laboratories, such as flow cytometers, utilize photomultipliers to determine the relatively concentration of various components in blood samples in combination with the optical filters and incandescent lamps. An array of photomultipliers is used in gamma camera, and photomultipliers are typically used in the direction of flying spot scanners. The next kind of photo sensor instrument is photoconductive cell. Photoconductive cells are light sensitive resistors in which resistance decreases with an increase in the light intensity when illuminated. Light striking the surface of a material can provide sufficient energy to cause the electrons within the material to break away from their atoms. Thus, free electrons and lots of charge carriers created within the material, and com- consequently its resistance is reduced. This is known as photoconductive cell. Now coming to the construction and working of this photoconductive cell, the light sensitive material is arranged in the form of long strip zigzagged across the disc shaped base. Please refer to the diagram which is to your right. The connecting terminals are fitted onto the conducting material on each side of the strip. They are not at the ends of the strip. Thus, the light sensitivity material is actually the short wide strip between the two conductors. For added protectors, a transparent plastic cover is usually included. Cadmium sulfide (CdS) and cadmium selenide (CdSe) are two materials normally used in the photoconductive cell manufacturing. Both respond rather slowly to change the light intensity. For cadmium selenide, the response time is around 10 ms, while the cadmium sulfide it may be as long as 100 ms. Temperature sensitivity is another important difference between the two materials. There is a large change in the resistance of the cadmium selenide cell with changes in the ambient temperature. But the resistance of the cadmium sulfide remains relatively stable. As with all the other devices, care must be taken to ensure that the power dissipation is not excessive visible light. For cadmium selenide cell, the spectral response is the longer wavelength end of the visible spectrum and extends into the infrared region. CDS photoconductive cells are often referred to as light dependent resistors LDR. They function within the same general spectral range as the human eye and therefore widely used in applications where this type of spectral response is required. This change in resistance may be large and several 100,000 ohm from the darkened area to only a few hundred ohm to the sunlight. So embedding the conductive path within the semiconductor substrate in a zigzag pattern will enhance the level of the resistance. In addition to the increase in dark resistance, this the same pattern will reduce the current as well as changing the output current to above the milliampere per hour. Now coming to the applications, when a photoconductive material is connected to a part of the circuit, the functions as a resistor whose resistance depends upon the light intensity. In this context, the material is called photoresistive, also called as light dependent resistor or photoconductive. The most common example of the photoresistor is a photodetector, that is device that measures the light intensity. Now photoresistors are not the only type of photodetector. Other types include charged coupled device CCD, photodiodes and phototransistors, but they are among the most common. So some photodetector applications in which photoresistors are often used include camera light meters, street lights, clock radios, infrared detectors, nanoparticle system, and low dimensional photo sensor devices. So these are all some of the uh, applications of photo sensor instruments which are being used in biomedical field. Thank you.